This conference is called Container Stack, and I thought in this talk today we've heard lots of things about running applications on containers and about sort of war stories of running containers. But how about we go right to the sort of bottom of this stack and look at exactly what a container actually is. So I'm going to build one from scratch with some code. Has anybody seen me do this before? Couple of hands, great, excellent. You can, help me out when I go wrong. How many people here actually write code from time to time? Excellent, great. And how many of you are Go programmers? Great, you're my peer reviewers, thank you very much. Right, so Sebastian gave me a very nice introduction. I work with a company called Aqua Security. A couple of my colleagues are here. And you'll find them outside. You might want to go and chat with them because they have a few copies of this book to give away. I'm the co-author of this book about Kubernetes security. So aside from knowing a little bit about how containers work, I know a few things about security and some things that you can do to improve your security. So find somebody with an Aqua shirt and you may be able to get hold of a limited number of copies that they've been able to... Actually, the number of copies they've been able to get through Swiss customs, I think, was the issue. So we're going to build a container from nothing in Go. And we're doing this to illustrate the three things that go to make up a container. Sometimes you'll hear people say containers aren't really a thing, because they're not like a first-class construct in Linux or in anything else. They're made up from these other constructs, namespaces, changing the root directory, and C groups. So hopefully, in this talk, I'll show you what those three different things are and how they contribute to what we end up calling a container. And hopefully, you will leave with a very clear understanding of exactly what a container is. Okay, so the first part is namespaces. And namespaces are what a process can see. So when we start with a process, and we start assigning it to namespaces which restrict some set of things that that process can see. So, for example, you might have a namespace for process IDs, and if your process is in that namespace, it can only see the process IDs in that namespace. So that's the first bit we're going to code up. Okay, I think this is going to need to be a bit bigger, isn't it? Maybe not quite that big. How's that? Is that pretty visible? Good? Okay. So when you run a container under Docker, you do something like docker run, the name of an image, and then you might pass in a command and maybe some parameters. And I'm going to do the same thing in Go by running go run main.go is going to be my equivalent of Docker. And then I'm going to pass in a command called run. I'm actually going to skip the image bit in my version because you'll see what I'm doing for images. And then I'm going to allow us to run some arbitrary command, maybe with some arbitrary parameters, in my process that I'm gradually going to containerize. I know it's a comment, but it worries me that I haven't closed those process. Whew, weird. Okay, so we're going to start with a main function. And the first thing we're going to do is look at those arguments that we're going to pass in. So we're going to start with, we're looking for run. So if I get run as that first argument, I'm going to call a function called run. And if anything else happens, basically it's a disaster. Not production quality, okay? Okay. Give me an hour and a half for that. That'll be a longer talk. Okay, so we need a run function. And let's start by having a bit of debugging. We like a bit of debugging. So we'll just log out what's going to happen. We're going to be asked to run basically everything in the arguments 2 and beyond. Okay. So I haven't done anything here. Literally all I'm going to do is print out some arguments that I'm supplied. But let's just check that we can run this. Okay. So let's make this a bit bigger. I am running this in a Vagrant virtual machine on my Mac. Okay, and hopefully, yeah, there it is. So I can do go run, main.go. I've got to say run, and I could say something like echo hello Zurich. And it's just logging out the fact that I'm going to ask it to echo hello Zurich. It's really not very impressive so far, is it? Okay, so let's have it actually execute this arbitrary command that I'm passing in. And we do that in Go by saying we set up a command structure and we want it to run whatever the executable is that's in argument 2, and maybe there are some other parameters, arguments 3 and onwards. Okay, we also have to wire up stood in, stood out, stdr. Otherwise, we wouldn't be able to see what's going on, and that would be really dull. And hopefully, I can copy this and then do the excitement that is multi-cursors. Yay. Whew. Oh, it's so good. Right. So this sets up a structure that is called CMD that describes the command I want to run, and then when I actually want to run it, I do cmd run, and that should execute my command. I'm going to just add in, I've got this little function here that checks for any errors and panics if anything goes wrong. I'm just going to wrap my, oh, it needs to be capitalized, run function in that. Okay, so hopefully this is actually going to run whatever I'm asking it to do. Let's find out. Oh. Args. Where are my reviewers? Okay, so not only do we get a log line telling us it's going to echo hello Zurich, we can see it actually echoing hello Zurich. Okay, so I can run some arbitrary executable. I could run a shell, like so. It tells us it's going to run bin bash. You can't really see what's going on, but if we run ps, we can see, well, there's a new instance of bash that I've just started, and I've also the one that I'm inside the shell of. And if I do exit, okay, back to normal. Right. So I want to start containerizing. I can run some executable. I would now like to start containerizing the process in which I'm running it. So I'm going to start applying some namespaces. And the first namespace I'm going to apply, it sounds really, really fancy. It's called the Unix time-sharing system. It sounds really, really complicated, but actually the only interesting things it does is allows you to isolate the host name and the DNS name. So I can give my containerized process a host name that will be different from the machine it's running on. So I can set up these namespaces. I think I said we set them up with syscalls, and I'm going to describe them in a system call attributes that I pass in when I'm going to run this new command. So syscall, sysproc attributes, and it's called clone flags. Clone is the system call that's actually creating this new process that we're going to run our executable in. And I'm going to ask for a new Unix time-sharing system. Okay. So now, if I run my shell, okay, and currently the host name, it's inherited the host name of the parent machine, but I could change that. So I could call it Zurich, let's say. Check that that has stuck. it has stuck, but if I, on the same virtual machine, the parent virtual machine is still called Vagrant. I can change the host name for my container, because it's starting to look like a container now, without affecting the parent host machine that it's running on. Practically got a container here already. But it would be nice if we could tell more easily when we're inside this container. One thing that you often do when you're on a different machine or inside a different container is you want to change the prompt to pick up host name and display that to you. So it would be nice if instead of it saying root at Vagrant, I could set this to say Zurich or container or something. And you might think we can do something like set host name. And I might call this, well, yeah, let's say Zurich again. Why not? This needs to be a slice of bytes. Okay. The trouble is, if I do this here, where I've put it, it's too late. This would only get called after I've returned back from running whatever my executable is. So that's no good to me. And if I do it beforehand, so if I do it here, I haven't actually created my process yet. The process gets created as part of this run function. So neither of those is any good to me. So we're going to do a trick. We're going to call this twice, or something like this twice. So, 2 copies. So the first one I'm going to call run, and it's going to be setting up the namespaces. And I'm going to have another version called child, and this isn't going to set up any new namespaces. Let's move that to there. Okay, right. So what I want to do is call this program again, right? And the second time I call it, I want to, instead of having the parameter run, I want to have a parameter child. And on that occasion, I will call the child function. I need to slightly change this. So I want to call this program again. And there is a very convenient thing called proc self exe, which is the program we're currently running. I'll show you this in a moment. So I want to call this program again, but I want to pass in child as argument 1, and then I want all the other arguments 2 and beyond. But because it's Go, I have to do a bit of syntax. So we have to turn this into a slice of strings. So I start a slice of strings that starts with child, and I append all the arguments 2 and beyond to that. Oh, I need to say it's strings. Right. Okay. So I'm going to run this program. The first time around, it's got the parameter run, so it calls the run function. The run function is going to create the new namespace, and it's going to create a new process in which it's going to run the same program again, but substituting the parameter child instead of run. So that time, it's going to come through, run child, and this time, we're going to set the host name, and then we're not going to have to set up any new namespaces again, and we're going to run the actual command that we tried to run, that we wanted to run. Okay. So, right. 2 cool things happened. The first is that we saw 2 sets of logging, because there's one inside the run function and one inside the child function. And also, yay, we have set the host name, so I can much more easily tell whether I'm inside my container or not. I currently am. Let's just check that we didn't mess with the parent machine. We didn't. But I can do things like, if I sleep for a little while inside this container, from the parent machine, I can see that function, that process rather. Yeah? A process inside a container is a process on the host. They're just like normal processes, and they're as visible on the host as any normal process is. Okay? So containerized processes are just processes. Okay, so let's quit out this sleep. Now, if I was inside a professional or production quality container, and I did something like PS, I would only be able to see the processes inside my container, but as it is, I can see stuff outside, and that's not very containerized. So we want to use another one of these namespaces, and there is one for process IDs. So we could just add it in here and say, I also want a new process ID namespace. If I'm going to create my process, it's going to be assigned this new namespace for process IDs. And they're actually going to start numbering from 1. Just like when you you boot a machine, there's a process called 1, or numbered 1. I think it would be nice if we could see the process ID. So let's add that to what we log out. Get the process ID. And we'll do that in the run function, and we'll also do it in the child function. Right. Okay, so I need to quit out of my container and run it again. Right, so we can see that worked. We can see the first function was running with some high numbered process ID, but when I created the new namespace and then created a new function, a new process with that process ID namespace, it's got process ID 1. Great, brilliant, job done. Except, if I do PS, we still see all of these processes, and they've got high numbers. And where's my low numbered process ID 1 in that list? The reason why this is showing me, it doesn't look very consistent with this new process ID namespace. And it's because when you run PS, it's not doing some kind of magic, I don't know, API call to the kernel. It's doing it through what's called a pseudo file system. And that pseudo file system is called proc. And if we look in /proc, we can see that there are entries for every running process on the host. We also might see proc, if I can find it, here we go, proc self. Remember proc self exe? So if I look at proc self, you can see that's a link to a process that happened to be 3245. If I do it again, it will be a different process number. So this information inside /proc is getting dynamically populated with information about running processes. If I run PS inside my container, I want it to look at a version of this proc pseudo file system that knows about my new process ID namespace and that only has information about the processes in that process ID namespace. And to do that, well, I can't just point it at the /proc on the host. Maybe I want my own /proc inside the container. And to do that, I think it's time we talked a little bit about changing the root. So it's a very simple call called chroot. It changes the root directory to point to somewhere within the host's file system. So once I've changed the root to point to somewhere inside that directory structure, that is the root. It's going to be the root from the container's perspective. And it can't kind of go any further back up the tree again. Root for the container is going to that it's root. It's the root that it has. So what are we going to point it to? I happen to have a copy of, where am I? Something called Ubuntu. If I look what's inside my Ubuntu directory, it's a copy of an Ubuntu file system. I've put a little file in here called root for container so that we can distinguish it from what's inside root on my host, where, I don't know if you can see that, it's got a root for VM. So we can tell the difference between my root on the virtual machine and what I'm going to make into root for container. So what I want to have happen is that when I'm inside my container, at the moment, when I look at root, it's still seeing the host's root file system. And I want to use chroot to point to the container root file system. And it's super simple. All we need to do is, actually I'll put it in a wrapper. So we just do chroot to vagrant Ubuntu. I'm actually going to do one more thing, because it turns out when you change the root directory, it leaves you in some undefined directory. So it's a good idea to explicitly change the current directory somewhere. It might as well be root. Okay. So now, if I run it again, and I do ls-root, it's pointed at that directory. That looks like root. I can't go any further back. If I try to go further back up the file system, I can't. There's nowhere to go. I'm still in root. And I've got my own proc here. I don't know if you can see it, but it's a proc directory. Okay. I would like a show of hands. If I do ps, am I going to see the processes on the host, or am I going to see the processes in the container? Hands up if you think I'm going to see processes in the container. Okay, about half of you are optimistic, and you're not far off. You're not far off. Doesn't quite work. It tells us what we need to do. The last thing we need to do is tell the kernel to treat this proc directory as a proc type pseudo file system and do the stuff to populate it with information about running processes. So that is also pretty straightforward. It's another system call. So I'm going to mount, and it's critical you get these parameters in the right order. Proc. Okay. When I've finished, I'm going to unmount it as well, because otherwise they just pile up and become really annoying. So I'm just going to unmount it when we're done. Okay. Quit out of my running container. Run it again. Okay. Are we feeling lucky? What do you reckon? Is it going to work? All right. Yeah! Okay, so we have containerized the host name, the Unix time sharing system, and we've containerized process IDs. One other thing, we're doing okay for time, aren't we? So one other thing we could look at is the containerization of that mount point. So if I run mount inside my container, I can see that proc that we just did mount for. On the virtual machine, proc, what am I doing? Mount. There's tons and tons of mounts set up on the host machine. One of which, down here, the last one, is the one that we can see from inside the container. We can see it from the host's perspective, right? We see /vagrant/ubuntu/proc, because that is what that directory is called from the host's perspective. Now, that's fine from my use here. But if I have lots and lots and lots of containers, it might be kind of annoying to have your mount on the host full of whatever mounts are mounted inside your containers. So we can kind of isolate this in the other direction. It's kind of slightly different. So we can say, I would like another new namespace is called .clone, and it's just called new NS for namespace. Apparently, this was the first namespace that was added to the kernel, and I guess they didn't anticipate how successful this whole new namespacing thing was going to be, so they just called it namespace, but it really means mount namespace. This isn't actually sufficient to do what I want to do. I also have to do unshare flags for this, and this is to do with basically not making the mount visible to the host, which is what I'm trying to achieve. So the container has its own namespace for the mounts, and it's not sharing it back to the host. So quit out of my container, run it again. Actually, let's just check that if I do mount and I grep for proc ones. So there's a couple of mounts on the host related to proc. Inside my container, there's my containerized proc mount. But now on the host, we can't see it. Before we could see it, but because of that unshare flags, now we can't see it. So we can keep all our mounts nice and tidy inside our containers with that particular namespace. Okay. You can sort of imagine that you can do the same thing with networking namespace, so that I can have a different set of network interfaces that are visible inside the container compared to what's visible from the host. There are also namespaces for IPC, inter-process communication. I think I've forgotten one. There's one more. User IDs. User IDs is interesting because the user IDs, it's not like they are completely new users. The users are visible from the host. If you create a user inside a container, it's kind of like processes. They're still the same users, but they can have different numbers inside, different identifiers, if you like, different names, in fact, inside a container. Okay, so namespaces are helping us limit what a process can see. And chroot also kind of limits what the process can see in terms of the file system. And there's one last thing that goes to making up a container, and it's C groups or control groups. Control groups limit the resources that a process can use. So not what you can see, but what you're allowed to use in terms of things like how much memory, how much CPU, how many processes, how much I/O you can use, all sorts of things. And they use another one of these pseudo file system interfaces. And here we go. So actually one quite nice way of showing this before I kind of code it is to run a Docker, run an actual professional container. Let's go to sysfs C groups. So this is where the different types of C groups are configured. And let's look at memory, for example. Let's go into memory and have a look at what's in there. And there are tons of different parameters. Some of these are configuration parameters. Some of them are kind of reporting information back so you can read them. And if we look at, for example, memory limit in bytes. So if I cat that, it's a very, very large number. That's basically all the memory available in this machine. So in this kind of default C group, memory is unlimited. The way this file system works is sort of it's hierarchical. So you can create a subdirectory. There's one here already that Docker has created. You can see it there in blue. And if I run, actually, let's just list what's in Docker at the minute. There's another set of all these parameters. So these are the parameters that are inside the memory C group called Docker. But if I cap the memory limit in bytes again, Docker is defaulting to basically unlimited memory for its containers. But if I do something like Docker run, I want it to be interactive, and if I limit memory to 10 megabytes, and I'll just run Ubuntu and a shell. Okay, don't worry about that swap message. So I'm running a container. If I now look inside the Docker directory, just make this a little bit bigger, I think, if I can, yeah. There is a subdirectory here that corresponds to that container. So when Docker created this container and it gave it this kind of random ID, it created a C group, which is basically a directory, with the same identity as that container. And if we look inside there, so cat docker 2b whatever, if we look at the memory limit in bytes in there, it's much smaller, and that's the 10 meg memory limit. So when Docker started that container, it created this directory, and it wrote into this memory limit in bytes file, that's the limit that I want you to restrict. So we can do the same thing, right? We can create subdirectories, create these parameter. There was one other thing I wanted to show you, actually, when I do that. So if I sleep inside this container, I hope I've slept for long enough. CD Docker, let's have a look. It's this 5.2 whatever directory. And inside here, as well as all the parameters, there are C group procs. And that tells us the process IDs that have been assigned to this C group. So if I look at that C group procs, there's only a couple of them. But if I look for that sleep process, grab sleep, my sleep process is 3611, and that is inside that list of processes that have been assigned to that control group. So by writing a process ID into this cgroup.procs file, we assign that process to the C group, and then it's got the constraints that are defined by all these parameters. It's kind of complicated, but it's not that complicated to write the code to do it. So I'm going to do it with a different kind of process. Let's just close this container before I forget. Okay. I am going to do it with the process IDs namespace. So let's look at that. We can see there's already, like Docker has got a C group in here. And I'm going to create my own C group in here. I've got some code to do this already to save a little bit of typing. Where's it gone? There we go. I'll just copy that. It's cheating, I know, but you know. So this function goes to that C group PIDs directory. It's going to create a directory called Liz inside that process IDs, which is basically creating a C group. And the interesting parameter for process ID, or PID C group, is the maximum number of processes that we're going to allow to run in this C group. And I'm going to say 20. You can run 20 processes. And I'm also going to assign whatever the current running process is. So here we go, we get the current process ID, and we're going to write that identity into that cgroup.procs file. Okay. So I need to actually do that. Create my cgroup, call that here. Okay. So that should mean my containerized process is in a control group that is limited to 20 processes. Okay. Okay. Okay, so now if I look in here, we should see a Liz directory. There it is. If I go into here, we should see that the maximum number of process IDs is, or processes rather, is 20. So I shouldn't be able to run more than 20 processes inside this C group. Anybody recognize that? Okay. That is a fork bomb. That is, it's a type of attack. I'll show you what it does. So, what we're doing here, I'll make this a little bit bigger. We're defining a function called colon. And inside that function, we call colon, and we pipe the results into colon, and we run it in the background. So that colon function just going to keep creating new instances of a colon function, which are going to keep creating more of them and pushing them into the background. And then all I have to do is invoke it the one time. Let's hope I've done this right. Okay. We pretty quickly see that it's unable to create resources because we've hit the limit of this 20 process ID limit. If I look at all the processes running on the machine, we'll see, yeah, there are quite a few defunct processes inside of Bash, but there will never be more than 20 of them, fortunately, because I can still type into my virtual machine. If I hadn't got this limited, all my resources on this virtual machine would have been eaten up by that fork bomb. So by the use of control groups, we have successfully prevented, you know, it's like a kind of denial of service attack, right? It's eating all the resources on the machine. And that's why we use C groups. We use them to prevent malicious or inadvertent excessive use of resources, which could starve, you know, if one container could starve another container or the host. That would be really bad. And if we look inside the C group procs, that's just going to be the parent processes. And if we look in the tasks, there's probably going to be a bunch of other IDs as well, a few other IDs. Okay. I've been able to stop that, which is pretty, you can't normally do that if you have a fork bomb. Okay. So, we have successfully used namespaces, chroot, and control groups to containerize a process. Containers are just processes. That's why you see containers are Linux. Linux is containers. They're just Linux processes. But we can use those constructs to isolate various features of those processes from each other, which kind of looks like containers. That's kind of what it's doing. If you want to play with it yourself, the code that I just wrote, there's something that looks extremely similar to that on GitHub. So you can experiment with it to your heart's content. I also thought I'd just mention a couple of other sort of only slightly related tools, but we have a couple of open source tools for Kubernetes security testing called Kubebench and kubehunter. And if you find my colleague Andreas, he was talking about setting up some demos outside. So you might be able to get him to show you those in action in a break later on. Okay. With that, any questions? Questions? No? Clapping is good. Thank you.